So I will start with this contour theorem. I'll prove it in great detail again. So before the Chinese New Year, we have done this. So there's one slide with 5 lines, right? So the 5 lines actually show the theorem. But now I want to do it in 5 pages or something. So the reason I want to go through this is, number one, lots of people ask me. So after the class, or some of your classmates wrote to me emails, they asked for this theorem. So to respond to the queries, I want to do it. There's another reason. So this is a beautiful theorem. So this is probably I guess, maybe the hardest theorem in this course. Although it can be written in a very short, like 5 lines, but actually is quite involved, right? So this theorem shows mathematics is not just calculation, memorizing formulas, and do manipulation of symbols. So mathematics is very, very creative, and you need your imaginations, right? So that's why I want to spend some time to talk about this contour theorem, okay? So here's a statement. Okay, so for set X, we want to show the cardinality of X itself is strictly less than the cardinality of the power set. I will remind you the power set in a moment, okay? So for example, let's look at simplest example. Suppose I have a set X which only has which only has 3 elements, A, B, and C. Now, what is the power set of X? Right? The power set of X, now by definition, it collects all the subsets of X, right? So let's collect the subset of X starting from the subset has no elements, then have 1 element, 2 elements, 3 elements, right? So the subset of X has no element is denoted by this symbol called empty set, right? Now if I collect the subset with only 1 element, I get A, B, and C, right? Now if I collect the subset of X with 2 elements, I get AB, BC, and AC. If I collect the subset of X with 3 elements, and then there's only 1 choice, that's X itself, right? So altogether I have these. Now in a situation of finite set, we can really see from these that the size or the cardinality of X, which is 3, is strictly less than the cardinality of power set of X, which is 8. Right? So this part is no problem. Now, how about the general case? Right? So now let's look at the general case. So the set may not be finite anymore. So we cannot list out all the elements and really count them. So the contour theorem says it's still true, right? But we need a different argument. Okay, so first I want to remind you the elements in power set is a subset of X. So this simple picture may help. So here on the right-hand side, I have power set. On the left-hand side, this the blue or black thing is a set of X. So now each point in the power set, right, like this dot Y, is actually represent a subset of X. So if I draw the same Y here, it becomes a region. So here is 1 dot. If I move to the left, actually it's a region. It has lots of dots, right? So I hope this is clear. We are going to use this in a moment. So every element in the power set is a subset of X. So if you draw from the Venn diagram, each dot here is a area in the left-hand side. Okay? Okay, so now so here's the start of the proof. We want to show the size, the cardinality. Okay, I point to here maybe. So the cardinality of X is less than the cardinality of power set, right? So I want to show the less or equal to, and then I show not equal. Okay? The less than or equal to is easy. So by the definition of less than or equal to, we only need to find injection of X into power set of X. The injection, you can see, you can just send any, I don't know why. Probably it's not because of this, right? You can send any element A to the set of A, right? So this is an injection. I guess this is quite easy. So I don't need to spend time on this. The hard part is to show they are not equal. Okay. I want to show that the cardinality of X is not equal to the cardinality of power set of X. So by definition, this means there is no perfect matching between the elements of X and elements of power set of X. So the mathematical jargon is there's no bijection from X onto power set of X. Oh, okay. If anybody knows what's going on, please help me. Right? So I don't know what's. Okay, so I want to convince you that X is not the cardinality of X is not the same as the cardinality of power set of X. So in order to achieve that, I'll show this. I'll show that any function, right? We are talking about bijection between X and the power set of X now, right? So I want to show that any function from X to power set of X is not surjective. You cannot cover every point inside power set of X. This is extremely similar to the diagonal argument. So any function from natural number to the real number between 0 and 1 will miss some point. It's not a surjection. Okay, so I'm going to do the same. Yeah. Maybe the paper touched these. Okay.
Move this to right a bit.
This is hard to move.
No, just change the signal in input source. Okay. Where's the controller?
Probably we use that. There won't be too long. Nice. Okay, that's just for
Okay.
that.
We just stick with that.
Please. Okay, thanks. Okay, here. I want to convince you that any function, no matter how clever you are, so now we are on one side, our opponent is on the other side, right? No matter how our opponent, how smart he is, any function f from x to power set of x is not surjective. I want to convince you of this. Okay. So now how do we do it? So here, so let's imagine that our opponent give us a function, right? So this f is the function our opponent give us. He says this function is from x to power set of x, right? Now what should we do? We should demonstrate, so we must demonstrate a point and tell him, okay, you miss this point, right? Because we claim that any function will not cover every point. So if somebody give us a clever function f, we have to return him a set, right? Some point here, and tell him that, okay, this set is in your targeted region, but you missed this point, right? So therefore, you are not surjective. Okay, so far so good, right? So this is what I want to do. Okay, f is given, f is there. So now it's my turn. I'm going to return him the set, this dot, s. Okay, so you are with me, okay? Okay, so now we go back to x, and we look at each element of x and decide whether we should put this element into S, right? Because S, this dot, will be a region here. As I remind you before, any dot here will become a region. So I must draw a region here. I want to go through every element in X. So I want to construct my S by going through every point in the set X and decide whether the point is in the set S or not in the set S. Okay? So let me repeat. I will look at element in the capital X, right? Look at each element, and for example, the element U. I'm going to decide whether U belong to the set S or not. Okay? So now the choice of, so the decision is made by something like diagonal argument, right? So here, so for example, let's look at this element U. This is just an example, right? So this element U, F will definitely send U to somewhere, to FU, because F is a function with domain on the left-hand side. So every point, he must shoot an arrow, okay? So let's say he shoot an arrow to here, F of U. Now remember, any dot here is a region here. So let's assume this dot, right, I'm pointing at, is corresponding to this region. Let's just assume. It happens to be that case, okay? So this case shows the element U is not inside the region, right? So this is the case. So in this case, if this point is not belong to the region FU, and then we do the opposite, right? We want to, remember the diagonal argument is like doing the opposite of what the other guy does. So we are going to do that. We are going to do the same thing. If U is, if f of U do not take U, we take U, right? So if in this situation, I will put the element U into the set S. I'm constructing. Okay? Now, maybe the element is not like that. So maybe I have another element V. So let's go through every element, right? Some element may behave like U. Some element may behave like V. So let's see. Suppose I take element V, is this black dot. Now again, F will send it somewhere, right? So F, let's say F send it to F of V somewhere, which is this red dot. Now again, the red dot will become a region on the left-hand side. I didn't shade it because I want to keep the V and the arrow. So you imagine this is a shaded region. So this picture shows the V is inside F of V, right? V is inside the red circle, which is the region corresponding to F of V, right? So in this case, if our opponent take V, which is FV take V, and then we don't take V, we will leave V outside the set S. Right? So we don't put V in S. Okay, so you do this for every element inside X. And then in the end, you get a collection. You get a collection of elements. So after we went through all the elements in capital X, we get the set S, right? Notice this S will be a subset of X because we collect elements of X, right? And by definition, this capital S is an element of the power set. Okay, so now we have this set S in the power set. Okay, so finally, we can go back to our opponent and tell him that your function f must miss this set I construct. Right? I already get a point on the right-hand side. Now I go back to our opponent and say, f didn't hit him. Okay? So we check that f must miss this set S. Okay? Now our opponent will say no, right? So our opponent say, I already covered everything. Okay, so we have to show he didn't. Okay? So let's see. So suppose our opponent say, no, I covered, I hit the set you just construct. So he says, okay, I hit the set S, right? So there is a Z somewhere so that the arrow shooting from Z is equal to S. Okay, so that's he says, okay? And then we challenge back, right? So we challenge, say, okay, our opponent give us this Z, said, okay, the arrow shooting from Z hit the dot. Okay, now we have to say you are lying, okay? So we challenge back. So we say, okay, good. So we have the Z, right? Now, S is a subset of X. Is the Z in S or not in S? There must be either in or not in. Now, the next page will say, no matter whether he answers yes or no, he is going to be in trouble. Okay, so that's the next one. So the next one is, okay, he could say that yes, right? Because we challenge him. Is Z in S? He could say yes, Z is in S. Okay, so then let's look at what happened logically, right? So if Z is indeed in S, and then Z must be in f of S. The reason, this means because. Okay, so it's because S is fz, right? Because he says the arrow shooting from Z hit S, right? So S is fz, so I can replace S by fz, right? This is just replace the things by the equal. Okay, so Z is in f of S. But when we construct a set S, we went through every element. If Z is taken by f of Z, we are going to leave out Z, right? So if this happens, then we do the opposite. We don't take Z, right? If Z is in fz, it's like the V. The regions cover the V. We didn't take it, right? So this is because of the way we form the set S, we must leave out the element Z. Okay? So this is the first case, and then there's something funny, right? Something wrong. Because you start from Z in S, and by the two lines, and you say Z is not in S. That's ridiculous, right? So it's a contradiction. Okay. Well, then our opponent may say, no, I just made a mistake. Actually, Z is not in S, right? So could be. Okay, let's try. So let's see what happens if Z is not in S. If Z is not in S, again, because S is f of Z, so I replace S by f of Z. So we are in this situation. Z is not in fz. So by the same, okay, when we construct the set S, if this happens, it's like the picture in the U in the picture. If Z is not in f of Z, we take Z, right? So from this line, we get to Z is in S. Okay. again, something funny, right? You start from Z is not in S, and then by logic, you get Z is in S. Something's wrong. So again, it's a contradiction. Now our opponent, I hope he will surrender, right? So the conclusion is, indeed, F missed this set S, because if he claimed that he didn't miss, then he's in trouble, right? So this shows that indeed there's no surjection from X to power set of X, so Cantor theorem is true, right? So I hope this, after 20 minutes, this explains the 5-line proof in one of the slides. Okay. Now we don't need to look at this anymore. Okay, so now this is our real topic, right? Counting. Oh, by the way, I do welcome your questions, right? So because people coming from different background, I don't care about those who are extremely advanced, right? But if you have queries, do ask me. So I will respond. Okay. So you include those who are watching webcast, right? So if you have questions, write to me, email me. I will answer. Okay. Okay. Good. So now let's move on to the to a less demanding topic. It's about counting. So we have seen some counting argument, but here we get more. We know more method. And okay. So there are several things we are going to count. So something like we arrange some object in a line in a row, or we arrange some object in a circle, right? And then the computation depends on something called permutation numbers or combination numbers. So we are going to, these are our tools to use. And then related to these topics, there's something called binomial theorem. So this is also something nice to know. And binomial theorem will tell us, in particular, the size of power set for finite sets. Okay. And also, in the end, there is a way to count certain things, like the roots on the rectangular grid. We will see what it is in a moment. Okay. So we have several. We'll look at some typical examples, and then we'll count them. We count the different numbers. Okay. Okay. So here, this is a motivating example because we like casinos, or we. So I download this from internet. So there's some game called poker, and then you win something, right, by playing this game. So I don't know exactly, but maybe some of you are good at this. So in poker, there are different kind of you get different patterns, right? So some patterns they're worth lots of money, right? So these things. So this is number 1. This is number 2. This is number 3 and 4. And so there's a ranking of these patterns. Okay. So now the question is, how many ways are there of obtaining these poker hands? So these are called hands. Okay. Right. So we want to count how many ways. How many ways we can get this royal flush. Okay, and so on and so forth. Like, how many ways to get this one pair? Okay, and then this is related, right? Why are they ranked in a way like this? So this is ranked number 1. This is number 2. It must be these things are less are rare, more rare than others, right? So this is probably too many. You have lots of chance to hit this. Right? So in the end, we'll count how many times you can get this. Okay. Okay. So let's start from the most basic things. So this is an extremely easy example. So suppose you have 3 hats, hats A, B, C, and 2 coats. Maybe in Singapore you never have any coats, but suppose you have, okay. Have 2 coats, coats 1 and 2 in your closet. So assuming that you are willing to do any combination of the hats and coats, okay. So how many different choices of hat and coat combinations do you have? Well, this is extremely easy. So I list out all possible combinations, right? So for the code number 1, I can have ABC. For code number 2, I also have ABC, right? So altogether, I have 6 choices, right? So this is fairly easy. But if you understand this, you understand this one. So in general, we can state a principle or a rule, right? Product rule, which we are going to use over and over again. Okay. So the rule says this. So this is just a fancy version of just now the hat and coat. Okay. So let me read this. So assume that a task can be broken up into 2 consecutive steps, like choosing coat and choosing hats, right? So if step 1 can be performed in N1 ways, in the example here, the coat you can choose in 2 ways because you have 2 coats, right? And for each of these, step 2 can be performed in N2 ways, right? For each of the choices of coat, you can have 3 choices of hats, right? So N2 will be 3, right? So the task itself can be performed in N1 times N2 ways, right? So because we have the same tree structure. So you have N1 branching here. For each of the node in this N1 branching, you have N2 many choices. So if you count this, it's just N1 times N2. Okay. Right, this is fairly easy. Now, well, we can even make it more fancy, but, well, let's just say it. So this is called the multiplication principle. So in general, if a task involves a sequence of m steps, right? Now you have 2 steps. Now let's assume you have 5 steps or 10 steps, right? So where the ith step can be computed in n sub I many ways. So then the total number is just, again, multiplication, right? So you just multiply them out, right? The same reason. So you have a tree. You can look at the structure of the trees, and the number of leaves are like this. Number of passes are like this. Okay. So the reason we can do this is because each step can be completed independently of the others. Right? I choose the code doesn't determine which hat I must choose. Right? If they are related, then this counting is not right. Okay. But in most of the situations, you will be independent. Okay. Okay. So let's do some warm-up example. So in Singapore, the car license plates are I hope it's like this. Whoever has a car can tell us, right? Okay, so the first letter is fixed, is Singapore, is S. And after that, you have a combination of 2 letters. So the letters are chosen from A to Z, okay? Now after that, you have 4 digits. So there are 4 digits. Each digits are from 0 to 9. And in the end, the last one is a single letter, also chosen from A to Z. Okay? So the question for you, how many possible numbers, how many possible number plates are there? Okay? So to get this plate, let's divide this into several steps, right? So this part, we have no choice. There's only one way of doing the first digit. So there are 26 ways doing the second one, and then 26 doing the third one, and then 10 to do this, 10, 10, 10, right? And the last one is 26. So the answer will be if you multiply them together, you get 3 copies of 26 BAA, right? These are the 26 to the power of 3 to get the letters. And also you have 10 to the power of 4 to get these, the digit parts. Okay? So the answer is this. This is just a simple application of multiplication rule. Okay, so now we can look at our first task. So we want to count the number of arrangements on a line, on a row. Okay? So the typical situation is this. So how many ways are there of arranging these n distinct objects in a row? For example, you put the numbers from 1 to n on a row, right? So how many different ways you can do this? Okay? I guess it's not too hard. So we choose objects to place in a row one by one from left to right. Okay, so there are n ways for the first position. Imagine, okay, right. So there are n positions. The leftmost position, you can choose any number from 1 to n, so you have n choices. After that, you have one less choice because you have taken one. So you have n minus 1 ways for the second position, and so on and so forth, right? So there are 2 ways, and so the last position, you have no choice. There's only one way. Now, multiplication principle, right? So the number of ways is just multiply everything together, which is n times n minus 1 times all the way down to 1. We are going to use this a lot, so we give them a shorthand. So we use the exclamation mark here, but it reads as factorial. So this is called n factorial. Okay. Sometime we are going to see 0 factorial. This formula doesn't apply, but we define it or we set it to be 1. Okay, just to make our life easier. Okay, this is okay. So this is called n factorial is a long product. Okay. Okay, so now let's continue to look at the different numbers, right? Arranging objects on a line. Okay. So the next example is this: in how many ways can you form a row of 3 different objects from 8 different objects? Okay, this sounds a mouthful, but right, you know what I mean. Okay, again, the same thing. So let's look at how you arrange the three guys, right? The first, for the leftmost position, you have 8 choices, right? And then after that, you have 7 choices for the second position, and then you have 6 choices for the third position. So you multiply together. So again, this is multiplication principle. You get this product. Hopefully I get it right. So it's this. Okay. Now, in general, this number has a notation. Okay. So let P of n and k be the number of ways of arranging in a row k different objects taken from n different objects. Just now we take 3 elements from 8 possible 8 elements. They are all distinct. Okay, so the number of ways is this: is n factorial divided by n minus k factorial. Does it make sense? Okay, so is this number 8 factorial divided by 8 minus 3, right? So divided by 5 factorial. Yes. So 8 factorial will have 5 times 4 times 3 times 2 times 1. Now, if you divide by 5 factorial, the tail is chopped off, right? So this is indeed this n factorial divided by n minus k factorial. Okay? So if you understand this, you understand that. So you have n factorial, but the last k terms, the tail of the k terms was chopped off because of this. You divide it by n minus k factorial. Okay? Now, this arrangement, why do we say this different object many times? Because so the order matters. If you swap the two objects, the arrangement is different. Okay, in a moment we'll see there's another thing we want to count. The order doesn't matter, but for this one, this order matters. You cannot swap. Okay. So we get a number called permutation, right? So this P of nk is called k permutations of n. Well, there are lots of equivalent. Okay, if you see different textbook, you see this. They all mean the same. Okay. All right. So now let's look at maybe one or two more examples, then we move on to the next topic. Okay. So let's look at this. So how many ways can you arrange 3 red, 4 green, and 5 blue beads in a row? So this time there's no word different objects, right? So we have, well, something are different, red and green and blue, but among the red, they are the same because they are the same bead with red color, right? Okay, so let's look at solution. So if all of them are different, and then we know the number of ways is totally we have 12 objects, right? So if they are all different, by the example we have seen before, we will have 12 factorial many ways. Okay? But now the beads between the red or between the green and between blues are the same. So we actually overcounted many things, right? So we have to remove these double or I don't know how many times counting. Okay, so imagine we have one arrangement already, but we know that all the red beads are the same to our eyes, right? So permute the beads of the same color will yield the same arrangement. So therefore, if you permute all the 3 red beads, it's the same. The same happen if you permute the green ones or permute the blue ones. So therefore, you have to count this. Okay. So there are 3 factorial ways to permute the red beads, right? And similarly, there are 4 factorial ways to permute the 4 green beads. And then there are 5 factorial ways to permute the blue beads, right? So the number of ways of arranging this is you have 12 factorial, thus we pretend they are different. Now you have to divide, right? Because each of these you have to identify the red beads and the green beads. So you have to divide it by 3 factorial, 4 times 4 factorial times 5 factorial. Okay, think of it. So right. So this is the way you remove the overcounting. Okay. Now this is the fancy version for this example. So you have many. So here you have 3 objects. Now suppose you have n objects. Okay. So I'll skip this. Okay. So now let's move on to the next variation of counting. So just now we count things on a line, on a row. Now we want to count things on a circle. Okay? So let's imagine that, again, look at extremely simple example. So in how many ways can you arrange 3 guests around the table? So here's a round table. There are 3 guests A, B, C. How many ways? Okay, so now the difference between arranging things on a line and arranging things on a circle is these 3 arrangements, if it's on a line, is different. Because, for example, this position, suppose I read from this position, I'll get A, B, C, right? And then this one I'll get C, A, B. This guy I'll get B, C, A, right? On a line, they give me different things. But on a circle, they are the same. Okay? So this is, in circular arrangement, the following are counted as one arrangement, whereas in a linear ways, these count as 3. So we have to identify these 3. In other words, we overcounted 3 times. Okay? So now you know, right? So now we can solve the problem by looking at this. So if we were arranging things on a line, on a row, it would be 3 factorial ways. Right? We have seen it several times. But now we overcounted 3 times. Just now I convinced you. So because these things are the same, right? So therefore you have to divide it by 3. So there are only 2 ways. Okay. In many textbooks, people get the same number using a different explanation. I think this explanation is also nice. So alternatively, you can imagine you are doing this. So because you have A, B, C, right? Mr. A could sit anywhere around the table. So you choose A as your reference point, right? So it's like the starting point of the line. So no matter where A is, that is the point you are going to count, right? Okay, so now you fix A as a reference point, and then there's only 2 ways to arrange B and C, right? Because B could sit on the left or on the right of A. So you have 2 factorial ways to arrange B and C. So therefore, you have 2 ways. Okay, so whichever way you prefer, that in the end it's just 2 ways in this case. Okay. Okay, so now let's look at a general case. Right, we always see an extremely simple example. If we understand the simple example, you understand this theorem. Okay, so in how many ways can you arrange n different objects in a circle? Just now it's 3. Now we have n. Okay, so you can do this, right? We can generalize the idea of the example. If they are on the line, you would have n factorial many ways. But now you have many times overcounting, right? Just now you have 3 ways. Now if you have n, imagine instead of A, B, C, you have A1, A2, A3, up to AN minus 1, up to AN. You have n objects. And then actually you have n circles, right? So you can rotate. You can think of this as a dial, right? You can dial it a little bit. You can dial it n times. It all create the same picture, okay? So therefore, we overcounted n times, right? Because the n picture we just imagined corresponding to 1 way, right? So we have to divide it by n. So the answer is n minus 1. You can also do it using the reference point, right? Imagine Mr. A, right? You just chase Mr. A. Where are you sitting? Okay, here. So after you nail down Mr. A, there are n minus 1 people to be arranged on the table. So this n minus 1 factorial. You can also do it in that way. Okay, so the answer in any case is n minus 1 factorial. Okay. Okay, so more examples just to consolidate our understanding. Right, so we look at more circular arrangement. So find a number of ways without removing any empty seat that 9 guests can be seated at a round table with exactly 10 seats. You have one empty seat, right? So there are 9 people you want to arrange. Okay, so what is the answer? Okay, well, it doesn't matter. So there's only one empty seat. Just treat them as one of the guests. Or the next example, we'll treat them as ghost, right? Suppose you have a good friend, ghost. So the empty seat was sitting by the ghost, okay? He is different from all the guests, right? So the empty seat could be treated as a new guest or new ghost, whatever. So then the number of ways is just this. Okay, the empty seat actually doesn't matter. Okay, now the next example, the empty seat matters. Okay, so find the number of ways without removing any empty seat that 8 guests can be seated at a round table with exactly 10 seats. just now we only have one ghost, right? Now we have two empty chairs. The two empty chairs now, they are the same. So we have to, this create a new situation, right? Okay, so just imagine, in addition to the existing guest, we have two different ghosts, right? So my friend, ghost 1, ghost 2 will also come, okay? So who will occupy the empty seats. Now, suppose they are these different ghosts, right? So then the number of seating is, we know, this 9 factorial, okay? Now, let's identify the two ghosts, right? Just now we say ghost 1, ghost 2, they are different, right? But now actually they are the same. So we double counted this thing. Okay. These two arrangement actually is 1, right? Because these are just two empty chairs, right? The picture are exactly the same. So in other words, we double counted twice, right? Every arrangement, we double counted twice, right? So therefore, we have to divide the whole number by 2. You agree? Right. So we get this number. Okay. Okay. Good. So that's about counting the arrangement on the line, counting arrangement on the circle. So now we want to look at counting some objects where the order is not important. Right. Just now I think I highlight one point says order matters. Now let's suppose the order doesn't matter. So in these situations, the typical example is like counting the number of subsets of a finite set. Because the element in the set, you know that whether you write ABC or or ACB doesn't matter, right? The number of elements in a set, how you write it doesn't matter. You can write it in different ways. They are the same set, right? Okay, so very often we count things like this. So here are some daily life example. So how many 5-person committees can be formed from a group of 8 persons? So inside the committee, there's no order. As long as you choose the 5-person, that's one way. You choose a different 5-person. Right, that's a different way. But among the 5-person, there's no first one, second one. Okay, so there's just 5-person there, right? Okay, so also, given n different objects, how many ways can we choose k of them? We don't arrange them on a line. We just want to know how many ways we choose them. Right? No more arrange on the line. No, it's not that part. Okay, so the key is the order doesn't matter now, right? Okay. Okay, so let's count. So we use this letter C. Just now we see P, right? P for permutation. Now this C, is for combination, or actually it's called binomial coefficient. We are going to see it in a second. Okay, so let C of nk denote the number of ways of choosing k objects from a set of n different objects. And okay, we don't arrange them on a line. You just choose, just pick. Okay. So then the number C of nk is calculated by this. N factorial divided by k factorial times n minus k factorial. Okay, this part, if you ignore the k factorial, that's exactly P of nk. Right? So we are going to use P of nk to show this. Okay, so why? So let's imagine that we arrange k objects out of n objects on a row. Suppose we not only we pick them out, we really arrange them on a row, right? Because we just learned how to count those things. So let's start from there. So and we count the number of ways of the arrangement using 2 different methods. And then in the end, we get the equation. So that's what we want to do. Okay, so the first method is use multiplication principle. just like we did. So the answer will be P of nk, right? You know that n choices for the first position, n minus 1 for the second, and multiply them, right? So you get this number. So this is the number we count using method 1. Okay. So now I want to count it in a different method so that C of nk shows up, right? Okay, so now let's count them in a different way. So let's do it in 2 steps. So the first step is we just choose the k objects out of n, right? So they are C of nk times. This is, by definition, this number is C of nk, right? After we fix the k elements, we arrange them on a line, on a row, right? So step 2, we arrange them in a row, so they are k factorial many ways. Again, this we know, okay? So now, by multiplication principle, the total number is this number multiply the step 2 number. So is this is the number of ways. So this is, we count the number of arrangement on the row using method 2. Okay. Now, no matter we count using method 1 or method 2 or method 3, whatever, they must be the same number, right? So therefore, we get this equation. This is counted using method 2. This is counted using method 1. They must equal because we are counting the same number, right? Same collection. So then you solve C of nk, you will get this is P of nk divided by k factorial, so it's this, right? So we get it, okay, right? Okay, again, we have a family of different notations. Not only we have these, we also have this. This bracket with, it's like a small matrix with n on the first row, k on the second row. So this is this number, the bracket nk, called n choose k. Oh, wow, it's very subjective, right? Okay, so there are some exceptions. So n choose 0, we define to be 1. The same as n choose n. Maybe n choose n is easy to understand, right? You have no choice. You have to take all. So this is only one way. N choose 0, probably is no choice, right? Okay, so just one way. Okay. Anyway, so now a quick observation. Let's practice, right, the concept. So I claim that n choose k is the same as n choose n minus k, right? Of course, you can use formulas. You can use a formula and check they are the same. But you can also use meaning, right? N choose k means suppose you take k objects in. It's just like leaving n minus k objects out. So this, the right-hand side is counting the ways of leaving n minus k objects out. And then it counts the same thing, right? So they are equal. Okay, so easy, right? Now, okay, so then we have examples. Okay, so how many different ways, how many different 5-member subcommittees can be formed from a 9-member specified committee if the president and vice president do not serve on the same subcommittee? Okay, so we have a board of 9 people. We want to choose 5. But there are some conditions, right? Among the 5, you cannot put both president and vice president in. Okay? Okay? So we want to count the number of ways. Okay, so solution. So there are 3 types of subcommittees, right? So type 1, let's say, it contains president but not vice president, right? How many ways? Okay. So you have to choose people other than the president and vice president to be in the subcommittee, right? The president is already in, so you have 4 empty seats to fill in. So you choose from the 7 people, which is 9 minus 2, right? The board of 9 people take away president, vice president. Okay, so you have 7 choose 2, 7 choose 4 many ways. Okay, now exactly the same. Suppose you take the type 2 says you take vice president but not take the president, you get the same thing. 7 choose 4. Okay. Type 3, this subcommittee does not have president and vice president. So how many ways? So among those non-president guys, you choose 5. So there are 7 guys, you choose 5, right? So this 7 choose 5 ways. Okay, so then here these are not in sequential because every, not bullet points, every type we finish the task. It's not we have 3 steps. We do first step, second step, third step. Each step, each type is a complete. It's a completion of the task. So here we just add, right? Because there are 3 possibilities. We just add. Hopefully the number is right. It's 91. Okay. Poker. Should we do the poker and then break, or break then poker? Anyone give me a yes or no? The poker and break, or the other way? Poker, good. So, okay. So let's count the number of hands, right? The poker. So the total possible poker hands are this. So from 52 cards, we don't have jokers. 52 cards, you choose 5, right? So this number in this lecture is not useful, but when we count probability, somehow the total number becomes useful. Okay, so anyway, so this is 52 choose 5. Okay, so you get this number, whatever it is. Okay. Now, how many this so-called royal flush? So these are from 10 to ace, right? How many numbers? How many ways to get this? Well, so there are 4 suits, right? The diamond, the club, the heart, and the spade, right? So each of them, you only have 1. For diamond, you have this. So you have only 4. So this is extremely rare, right? Right? The probability will be 4 divided by this is extremely low. Okay. Now, how about this kind called straight flush, right? So we don't, the royal flush we already counted, so we don't count them again. So how many ways? So again, there are 4 suits, right? For each suit, there are 9 straight flushes, right? Because you only have, if you start from lowest number, you have 1 to 9, right? The 10 will give you, will be there. So you have 9 straight flashes, so determined by the lowest card. So number of ways is just 4 times 9, 36. Okay? Okay, so then we want to count this. So 4 of a kind. So there are 13 choices for the 4 cards, right? So from number 1 to number 10, then you have Jack, Queen, and King. So 13. Now, then you still have, you have to put something here. So you have 48 choices, right? Because, for example, in this picture, is this a king? So the king is there, so you cannot pick king anymore. So you have 48 choices, right? So again, we use multiplication principle. You get this number, 13 times 48, right? The 13 is the number of ways getting the 4 of a kind, and then the remaining one, there are 48 ways. So by multiplication principle, you get this, okay? Now, how about this called full house, right? So these are a triple and a pair, right? Okay, so now how about the number of triples? So you choose the number, right? In this case, this is 8, right? So you choose 1 out of 13. Now, after you fix the number, you have to choose their suits, right? So it's 4 out of 3, right? So there are 4 ways, actually. So there are 52 ways of getting this triple. Not triple, the 3 cards, okay? And then after that, you have to get the pair. So you cannot use 8 anymore. So you have 12 possible number to choose. So you choose one of the 12. Again, the C of this 4 choose 2 is to choose a suit, right? So very often I will use C of 4, 2, or sometimes I use 4 choose 2. There's no deep reason, because if I type C42, I can save some space, so I can squeeze more things into a slide. You'll see that I use both of them, okay, from time to time. Okay. But is accounting all right? Right? It's all like this. Okay. So the next one, so you have this is called flash, right? So you get 5 cards all from the same suit, right? So there are 4 suits. For each suit, there are 13 choose 5 ways of picking 5 cards, right? But we have to take away those things we have counted, right? So we have to take away royal flash and straight flash. So we have to take away this, and we have to take away this. So we have to minus 40 of the number. So according to the calculation is this. You can check. Okay. And there are 2 more and some homework, right? So the 2 more is, okay, so this is called straight. So it's, okay, so here is from 10. So you have things connected, right? So there are 10 choices for the lowest number in the straight, and after you choose this, the number of the rest of the other 4 is fixed. You have no choice, right? So after you choose the lowest card, the card with lowest number, then the number is fixed. Okay, so you can only count the number of different suits, right? Okay, so but there are 4 choices of suits for each card, right? Because here you can have 4 choices, 4 choices, 4 choices. So altogether there are 4 to the power of 5. But we have to exclude these guys again. So you have to take out 40. Okay? Okay, so this is the last example, and then this part will, there are some big numbers are left to you, right? Okay. Okay, so now 3 of a kind. So this, you need a little bit thinking. So there are 13, okay. So we have 3, okay, triple, let's call it triple. And then these 2 are not a pair. These 2 has to be two different cards, okay? So there are 13 choices of number in the triplet, right? And for a given number, there are 4 choose 3 choices, right? So you get this number. You multiply this, you get that fix this part, right? Now, then we have to pick 2 cards from the remaining 48. But we don't want to have pairs, right? So you can choose, so there are several ways of doing it, right? So you can choose, first choose the number, which is 12 choose 2, right? So here you get number 8. Now for the remaining 2, you will not look at 8 anymore. So you have to choose 2 different numbers from the remaining 12 numbers. So it's 12 choose 2. Okay? So after you choose the fixed number, each number will have 4 possibilities for the suit. So it's 12 choose 2 times 4 times 4. And it turns out to be this. Okay, you can check on your. So the number is this, and the rest is tutorial. Okay, so let's take a break, and you can check whether this number is right. Okay. Okay, let's start a little bit earlier because I got some interesting questions. So one question I cannot answer. Oh, okay. So one question is about this straight, right? This. Okay, so one question is about this one. So the question is whether ace 2, 3, 4, and 5 count as straight flush. I don't know. I'm not an expert on poker. So whoever good at poker, tell us. So probably yes, right? So okay, so you can Google and probably. Okay, so that question I have to check. So so here, if you allow that ace 2, 3, 4, 5, you get 9. If you don't allow that, you have 8. So it's just like that. Okay. So now the other one is I'll show you the question. So the question is here. How do I get this, or where does the 2 come from? Okay. Okay. So so let's see. So what is? So we want to have. Okay. So we have 8, 8, 8, right? So for example, right, we have 3 of a kind, and then we have something different, right? Like x and y, and x is not y, right? So we want to count how many. So the 8, 8 could be 9, 9, 9. Okay, so I want to do this. Okay, so let's fulfill this in several steps. Okay, step 1. Let's fix the triplets, right? So we have 13 possibilities to choose the number. So okay, so the step 1, let's find the triplets. The triplet, okay? So the number of ways is 13. So that is the possible numbers. Right, because 8 is 1 among the 13. So you have from 1, from ace to 9, and also you have 10, jack. So you have 13, right? So you have, so this will be the number you fix, for example, the 8. And then not only that, you have spade, I don't know, you have club, you have diamond, right? So you have to determine the suites of the 3 cards. So you have 4 choose 3. You can also equivalently you can say which one I didn't take. So in this case, it's a heart, right? I didn't take heart, so anyway, so this is 4. So this is 52 times, 52 ways, just to fix this, right? Now, okay, for those who ask me questions, now, step 2 is what you really want. Okay. So I want to get the x and y. So there are several ways. So let's try one way, the way I just said. So now suppose you take 8. Then you cannot take 8 anymore. Because if you take 8, you get 4 of a kind. That's not good. So you have to choose from the remaining 12 numbers, you have to choose 2 of them. Right? Suppose you ruled out 8, you have 12 numbers. Then among the 12 numbers, you choose 2 of them. Are you with me? Right? So this is 12 choose 2. Okay, 12 choose 2. Right? Now, after you choose 2, then you get the number x and y. Right? And then the x could be a spade, or this could be a diamond. Right? So for x, you have 4 choices. For y, you have 4 choices. So altogether, you have this times 4 times 4. Okay? So what is this then? This is this times this divided by 2 factorial times 4 times 4, right? This is this number. Okay. So this is 48 times 44 divided by 2. So the divided by 2 is you take the 2 numbers because you 12 choose 2. When you calculate, you have to divide by 2. Okay. So we get this number. Okay. Now you can also do it in a different way, right? So after step 1 is wait. So is this okay? So I think this explains the number already, right? Now suppose you don't want to say 12 choose 2. Let's do it in a hard way, right? So after we do step 1, so here's step 2 prime. So alternatively, I want to choose from the remaining 48. Okay, so we choose 48 remaining cards, right? So it's remaining cards. Okay, so I choose 1. Right? So it's 48 possibilities. So that's probably x. X will be, so for it, maybe I take the king. Okay? So x is the king. Right? After I take this, I want to choose y. Okay, since I take king here, I cannot take king anymore. Right? Because, so I only have 40, okay, so this is that's for x. Now I have 44 remaining ones for y. Right? Because if I take king, I cannot take king anymore. So I only have 44 remaining cards. I choose 1. Okay? So step 2 will be I take x and y consecutively. So I'll get 42 times 44 number of ways. Wait, but where's divided by 2? Order, right? Because x, y, and y, x are the same. Right? So suppose the y now is jack. So king and jack, let's say, what do I draw? I couldn't see. The diamond king and the whatever jack, right? And if you swap, they are the same. So we have to divide it by 2. Okay, so that's why you have to divide it by 2. So you get the same number. Okay, so, well, you are younger, you are smarter, so it's just like this. Okay. Okay, so now we have to say goodbye to poker, although we like them, but. So let's continue, right? So we have other job to do. So the next topic will be binomial theorem. So after that, we'll count something on the grid. Okay, so, but these two are easier, I think. Okay, so the number, this number, funny number n choose k, is also called binomial coefficients. Since they appear in the binomial expansion of this a, if you calculate a plus b to the power of n, you get the coefficients, and these are actually is n choose k for some n, some k. Okay, so for example, you have seen this: a plus b squared is just this. Okay, I will not read. So a plus b to the power of 3 is this, and so on and so forth. Okay, so this is a, so in general, if you write many of them, you'll see that there's a pattern. So the pattern is called so this is called binomial theorem. So it says a plus b to the power of n. Well, the shorthand is this, is the sum of k from 0 to n, n choose k, right? N choose k, and a to the power n minus k, and b to the power of k. So okay, we don't understand what is this sum, right? So let's spell it out. So k from 0, k is 0, so it's n choose 0, which is 1, right? Just now we say. And then a to the power of n times b to the power of 0. So in the product, the degree is always n. So the exponent of a and b, if you add them up, always give you n, right? So this part, n plus 0 is n, right? Now the next term, when k equal 1, so you get n choose 1. And then a to the power n minus 1, then b to the power 1. So that if you add them up, you still get power n, right? And so on and so forth. The last term, all the way to the k equal n, which is n choose n. Now this time you exhaust all the a's, and then it's b to the power of n, right? So this is called binomial theorem. Okay, let's prove it. Okay, so proof, we just multiply everything out. Okay, so we multiply the n copies of a plus b using the distributive law, right? So you just multiply everything out. Okay, so in other words, we are going to choose one of a or b from each of the n factors of a plus b, because it's power to the n. So you have n factors. So each one, among each of them, you have to choose a or choose b. You cannot skip, right? So you either choose a or choose b. So multiply our choice in one to get the binomial a to the r, b to the s, right? So because you choose, for example, you choose r copy of a and s copy of b. Right? Okay, so then you have to add all possible choices. Okay, okay, so let's do the counting. So observe that this we just said. Okay, a plus b to the power of n is a sum of terms of the form a to the k, b to the n minus k. So here I cheat a little bit, but you will, the cheating was, here actually is b to the k times a to the n minus k, but they are symmetric, so right, so it doesn't matter. So it's of the form a to the k, b to the n minus k. So to get this term, a to the k n minus k, you have to pick k from the brackets, right? We need to pick k of the factors to contribute a. Right? Among the n bracket, n copy of factors, you need k copy of a. So you have to choose k many brackets. And those are the guys contribute to a. The remaining guys contribute to b, right? Okay, so the other n minus k will contribute to b. So therefore, there's n choose k many ways to get this a. Okay, so the coefficients of a to the k, b to the n minus k is cnk, right? You agree with this, right? So now, since I cheated, I should have n minus k here, but we just observed that cnk is the same as c of n minus k. So it's symmetric. So the argument really works. Okay. Okay, so now this probably you have seen this in JC or in Pauli or whatever. So this is called Pascal triangles. So this is a plus b to the power 0. The second one is a plus b to the power 1. This is a plus b to the power of 2, and so on. So the number in the nth row are the coefficients in the expansion of a plus b to the n. For example, if I do for the cube, right? So this is 1, this is a to the cube plus 3a squared b plus 3b squared a and plus b cubed, right? So these things are obtained, the numbers in the nth row are the coefficients in the expansion of a plus b to the n. Okay, now observe this. Observe the number in each cell is the sum of the numbers in the two adjoining cells in the line above. Okay, so here, 10. 10 actually is 6 plus 4, right? Choose another one, 15. 15 is 5 plus 10. Okay, one more. This one, 21. So it's 15 plus 6. So each number here is the sum of the guys on top of him. Okay? So now if I write in a combinatorial number, so this is the kth position in the n plus 1 row, right? Now on top of it, for example, this one, on top of it, this is the kth element in the nth row, right? The kth element in the nth row. And then this is a kth element in the n minus 1 row. This is a k minus 1 element in the nth row, right? Sorry, try again. This 35. This is the fourth element in this row, right? So I claim that this is the third element in this row plus the fourth element in this row, in the row above, right? So this is this. Okay, so we have this observation. Okay? Now can we prove it? Yes, we can prove it in two different ways. So let's prove this. Right? So here to save space, I write C of something. Okay. So what is left-hand side here? So the meaning of this is like the number of k-person committee formed from n plus 1 person. Right? N plus 1 choose k. You have n plus 1 many candidates. You choose k of them. Right? So this is this number. Now, how about the next, the right-hand side? So here, so imagine you are one of the n plus 1 candidates, right? So now let's count the choices in two different ways, okay? So you can count the number of possible k-person committee by, first, you count those committees which include you, and then you count those committees which exclude you, okay? So the committees which include you, the number is n choose k minus 1. Why? Because altogether you have n plus 1 candidates. You are one of them. So now you are separate. So you have n many remaining candidates, right? Now you choose k person. Yourself is already in. So you only have k minus 1 positions to fill. So is n choose k minus 1. That's the first case. The second case, so you want to count the number of committees which exclude you. Okay, so you have n person because you are out. You are not one of the candidates. So you have, originally you have n plus 1 candidates. You are out. So you have n candidates, but you have k position to fill. So it's n choose k, right? So therefore the right-hand side is just this. So you just add them, which is right-hand side. So they are equal. Okay. Now, if you don't like this clever argument or whatever counting argument, you can do it by brute force, right? You know the formula, so you just try the formula. Well, I don't want to try it. So in the end, you get this. Okay. So let's you can check the proof. This is correct. Okay. So now, as a corollary, we'll get the size of power set. So recall that if X is a set, the power set of X, P of X, is a set of all subsets. Just now, at the beginning, 1 hour ago, we are looking at a very complicated case like this. Now the question is, suppose X has n elements. Right? It's a finite set. How big? What is the size of the power set of X? Well, you'll see why we call it power set. why we call it power set. Okay. So now to form the power set, you take k element subsets. Right? Just now, remember at the very beginning, I give you an example of ABC. Right? So I count a subset of 0 element, I count subsets of 1 element, and 2 elements, and 3 elements. Right? We do the same. So for each of the k from 0 to n, the number of subsets of X of size k is Cnk, is n choose k. Okay? So altogether, okay, you'll start from the number of 0 elements, which is just empty set, just 1. Okay? And then you have n choose 1, right? N choose 2, and so on and so forth. So you add these. But can we simplify this? The right-hand side is a big sum. Can we simplify? The answer is yes. So if in the binomial theorem, you put A equal B equal 1, okay, so where is the binomial theorem? Where is it? Here. Okay. So if you put A equal B equal 1, this side will give you 2 to the n. Right? Now look at the bottom line. A equal B equal 1 means I don't need to look at AB anymore. So it's just n choose 0, n choose 1, n choose 2, all the way add to n choose n. Right? So remember that n choose 0 is the same as C of n comma 0. Right? So now 2 to the n is the sum of all these n choose something. Okay? So let's fast forward. Okay, so many. Okay, so we get the power set, the size of power set is 2 to the n. So probably that explains why it's called power set. It's like raising the power. Okay. Okay, the final topic of today, we are going to count something weird, something like this. It's also very interesting. Okay, so here we want to count the number of roots on the rectangle grid. Okay, so if we are allowed to go east and north, right and up, right? But you cannot backtrack. You cannot go down. You cannot go to left. So you can only go right or up, right? How many ways you can go from A to B in this figure? Okay, so you try to start from A. You can go, for example, you can go like this, or you can make lots of zigzag. Right. So the challenge is how many ways. Okay. So you need a clever trick. Okay. So the solution is a possible route like this, right? So you can follow like this. Okay, go east and north, east, east, north, east, north, east, east. Okay? So now convert, whenever I say east, you say 0, or you say 0. Whenever I say north, you say 1. Okay? So then it's a string of 0 and 1s. Right? So convert this path into a string of integers consists of 0 and 1. So this is 0, 1, 0, 0, 1, 0. Okay, so those things, right? Okay, so the 0, 1 string will correspond to this, right? 0, 1, 0, 0, 1, 0, 1, 0, 0. Okay? So the length of this string, this binary string code, right, because they only have 0, 1, is always 9, right? Because you have to go to B. So you have to cover horizontal distance and vertical distance. So you have, so it's always 9, which is the sum of the dimension. So here you have 6 units horizontally and 3 units vertically. That's why you get 9. Okay, so we are here, right? So now for this grid, the corresponding 0, 1 string always have 6 zeros and 3 ones. Right? This is because, as I said, you have to travel, you have to cover the horizontal ones. So you must have 6 of zeros. Right? You cannot backtrack, so you cannot have more. So you must have exactly 6 zeros. The same reason tell you must have 3 ones. Okay? Okay, so right, so this is the reason. So the required number of different rows is equal to the number of different 0, 1 strings of length 9. Right? So we convert this problem to counting the binary strings. Okay? So with 6, 0, and 3, 1. So we count the number of strings of length 9 with 6, 0, and 3, 1. Well, then that's very easy. So this is like choosing 6 different places from 9 different places to put the zeros. Right? So equivalently is like choosing 3 different places from 9 different places. This is like choosing ones. So the answer is just like this. So it is 9 choose 6, equivalently is 9 choose 3. No matter how you try, is equal to this. 9 factorial divided by, so this is n factorial divided by k factorial times n minus k factorial. Right? So we get this. Okay? Is this? So this is, right, if you don't see the solution, it takes a while to figure out this, right? It's not so easy. How do you count? I mean, move a few steps here and then up, and it's not so easy, right? But this is a very nice way. Okay, so the last example, and then we'll finish. Okay, so we want to have a slightly more difficult variation of the one. Okay, so we still have this the grid. It's like from 0, 0 to 8, 8. Okay, now how many possible bus routes moving east and north? Right, the same thing. Okay, without backtracking. Right, from 0, 0 to 8, 8, but you must pass 3, 3 or 5, 5. You must pass one of them. Okay, so can you imagine the? Okay, so this is my last time today to use visualizer. Come on. Okay, so I cannot draw accurate picture. So say this is 0, 0. So this is 8, 8. So now somewhere in between you have 3, 3. You have 5, 5. So the bus can go. You have to go either you go through 3, 3, and then you can do whatever you want to do, right? Or you can do something like this. You can, I don't know, you can wander around, and then you go to 5, 5, and then you do some funny things like this, right? This is also a possibility. Or you can pass both of them. Okay, so I must finish in 2 seconds. Okay, so you know then we have to use inclusion-exclusion principle, right? So it's okay, let's go through it really quick. So let's set A denote the set of routes from 0, 0 to 8, 8 that pass through 3, 3. Let B be the same pass through 5, 5. So what we want to count is the size of the union, right? Either this or that, right? So inclusion-exclusion principle. So the A is R. So do you know how? So because from 0, 0 to 3, 3 is 3 times horizontal, I mean 3 units horizontally, 3 units of, so it's 6 to 3, right? Now and then you have to go from 3, 3 to 8, 8. So that gives you 10 choose 5. Okay, so this is A. For B is the same thing. It happens to be they are symmetric. So So B is same thing, but A intersect B, you have to pass both 3, 3 and 5, 5. Okay. To go from 0, 0 to 3, 3, you have this many. And then from 3, 3 to 5, 5. 3, 3, 5, 5. 2 unit to the east, 2 unit up. So it's 4 choose 2. 4 choose 2. Now from 5, 5 to 8, 8, you get this many. Right? So altogether you have that. So then inclusion, exclusion principle, hopefully the number is correct, you get this. Okay, so that's all for today. Okay, thank you. Bye.